Hope my screen is visible to you all. Screen is visible? Hello?
Yes, ma'am, it's visible.
Okay, thank you. Okay, so today we'll review I'll start the class, okay? So today we'll see, we'll review the normal stress we have studied so far. Then we'll define and discuss the nominal stress, which is also called as engineering stress. Then we'll discuss what is true stress, and then we'll move to the strain part, which is normal strain. So this is the, let me note. Okay. So earlier what we discussed, we have taken a stress member. Okay, we have given a axial centric loading on this member, and the length of this member, suppose L. So what will happen when you stretch a member? Suppose if you stretch a rope, it will extend, it will elongate some. The original dimension will change. Is it or not? When you stretch a rubber band, suppose the girl used to used for their hairs rubber band. If you stretch a rubber band, what will happen? What used to happen? The cross sectional area around the what? Just a second. Okay, the cross sectional area around the section. Just imagine you're stretching a band. What the width of the section at the middle portion used to get stretched or not? The cross sectional area over this. Suppose consider this is a band. Okay, you are stretching the band in this direction. In tension, you are stretching the band in this direction and in this direction. What will happen generally? The cross sectional area used to become less here. Suppose your band is, this is the normal band. Suppose I didn't get any video, so hope this will, suppose this is a simple band, and now I'm stretching this band. You do it in your home, you stretch this band, then it will stretch and the cross sectional area will become less, it gets reduced. Okay, length used to become increased, but the area used to become decreased. Suppose your original band was this much. Your original band was this much. When you stretch, this becomes, let me, just a second. Suppose your original band was this much. When you stretch, it becomes like this. Are you getting my point? Your length becomes increased, but the cross-sectional area becomes decreased. It becomes reduced. So how much it gets elongated? How much it gets elongated? That is your, we are representing that by delta. So now the length becomes L plus delta. This was the original length. When we stretch the rubber band, it gets elongated to some extent, and we represented that as L plus how much it is elongated, represented as delta. Suppose the length was 6 meters. Now when you stretch, suppose it becomes 6.5 meters. So this delta will be your 0.5. Got it? So when we suppose we got the new length, which is L by delta. If you want to see what is happening inside the rubber band, let's do a transverse cut on this section. Let's cut this section. So what will we get? We'll get if we resolve the forces, we'll get a normal force and we'll get a shear force in this direction. And if we equate the forces, V is equals to 0, and we got, already we have discussed this part, but I am reviewing this part. So this P will becomes to N, right? For the transverse cut, what we got in the earlier classes, that your shear force will be equals to 0 and your on your normal forces will becomes equals to P. And we assume that all the stresses is evenly distributed over this section. Is it or not? For here shear force becomes becomes 0, negligible. Now this P becomes N, and the whole stresses on this area is uniformly distributed. So next, we got normal stress. What is normal stress? This is the normal force per unit area. And we have assumed that stress is uniformly distributed over this area. And for the sign convention, we have assumed that if the force is in tension, what will be the sign convention? It will be plus. If the stress is in compression, the sign convention we will use negative. For this tension we'll use positive sign, and for this compression we will use negative sign. So this is your normal stress. Now what is nominal stress and true stress? So basically in engineering purpose, we use nominal stress. Sigma equals to N by A naught, where your A naught is the initial cross-sectional area. And the for true stress, sigma is equals to N by A, which is the actual area becomes smaller than the when the specimen fails. What it is? Let me explain. Just now I told you, suppose this is the rubber band. Suppose this was used to be a rubber band. When you stretch and it becomes failed, what will happen? At some point when you stretch and then you leave it, it will reverse back to its original shape. When you stretch more, suppose after stretching for some time, if you applied a large force, it will deform to another shape. It will elongate and this thickness will reduced. Okay. So this area was A naught. Original area was your A naught, and the new area is your A. Okay. So nominal stress will be your N by A naught, which this A naught is this part. Before stretching, what was the initial cross-sectional area? You will take that area, and for this formula you get nominal stress, and this stress is used in your engineering problems. All we will get numericals in this class. So we take normally for structures and all this nominal stress. But sometimes they may ask you what will be the true stress. So your true stress will be what was the force acting on that, and what is the actual area becomes, what was the actual area which we get after the specimen fails. When this rubber band fails, the cross sectional area will gives you A. Hope you have understood what is nominal stress and true stress. In the true stress, difference is that in the true stress you will use the area which we get after the specimen fails, and here we'll use the initial cross sectional area, the area we have got before the structure or the member fails. I have taken an example of rubber. You can take any structural member, any member. If you I have taken the example of rubber because it is easy for me to pull out now and give you an example, but you can take any member. Okay. Now tell me which one will be bigger. Nominal stress will be bigger or true stress will be bigger? Response. Which stress will be bigger? Response.
True stress.
Why? Why it will? I have written here larger. That's why.
No, because once we stretch and it will it's harder to explain.
Okay, let me explain. See, okay, just tell me which one will be greater. Your A naught will be greater or A will be greater?
Not, ma'am.
Yes, your A naught will be greater. So when this fraction is greater, automatically this value will be less or not? right? When this value will be more, this value will automatically becomes less now. Now here A is less, so we'll get this value larger. So remember, always your true stress will be larger than your nominal stress. So with this, we ended with stress. So normals, we got three types of stress: normal stress, nominal stress, and true stress. Next, let's move to the strain part. Anyone can tell me what is strain? Without going with the definition, what is strain?
Change in length by normal length.
Good, very good. So strain is your change in length by original length. So we represent it by a symbol epsilon. And you know, there every year there is a question that strain is dimensionless or not. Many people get confused. So this will be a dimensionless quantity. How? See, first I'll discuss the what is the formula, then I'll move to this part. So here, elongation per unit length. So how much elongation we got divided by the original length. Suppose the original length of this was L. Okay. Suppose the original length of this member was 6 meter. When I stretched, it becomes fail at some point, and now the length comes to now the new length we get now the new length. Suppose we got 7. So how much is the change? Delta will be 7 minus 6, which is 1. There is a 1 change in length is how much? 1. So your strain will be 1 by what was the original length? 6. We'll get to some value. So that was the strain value. This is the simply normal strain. Change in length by original length. And how this becomes dimensionless? Suppose this will be in mm, and this will be, this suppose this is strain. This 1 meter, what is the unit? Suppose I am taking all this in mm. So this will be in mm. 6 is also in mm. So mm will cancel out, no dimension, so it will become dimensionless. Clear this part? Let me allow some students. Okay. So this part is clear. What is normal strain? Change in length by original length. And for this also we have some sign convention. Plus tension causes, when the elongation will be in tension, then we'll use positive sign. When there is a shortening, okay, there will be two situations. When you stretch this rubber, when you stretch this rubber, in this direction, that means tension. So it will become, after fail, when it fails, this will be the new dimension or new structure, you can say. But when you compress, when you apply compression, suppose this was the structure, when you compress like this, what will be the new? This will become this. The area will become more. Again, so shortening, here the structure elongated, here the structure becomes short. So for shortening, we'll use shortening, or you can say this compression causes this shortening. Then we'll use the convention of we'll use the sign convention of negative. When we'll pull out the structure, it gets tensed. Then there will be an elongation, and we'll use the sign convention of positive. So same along with In the similar way, we got normal stress, then we got nominal stress, and we got true stress. In the same way, we have normal strain, nominal strain, and true strain. Same here in the strain part, L depends. Earlier we saw there was L naught, so A naught and A. So same here, we'll change with L naught and L. So L will be your initial length. This will be your the actual length which we generally get after the deformation of the structure. So this will be a normal strain. In engineering purpose, we use this formula, change in length by that initial length, and this is your true strain. So I want you to do this numerical right now. Very easy. A flat steel alloy bar has an initial thickness of 10 mm and an initial width of 60 mm. It is subjected to a total axial load in tension of 60 kN. Determine the nominal axial stress in the bar. And another question is, a flat steel alloy bar has an initial length of 900 mm. When subjected to a total axial load in tension of 60 kN, the bar elongated by how much? 0.45 mm. So determine the nominal axial strain or engineering strain in the bar. Please do this numerical and let me know the answer. My screen is visible. Question is visible to you all. Do this numerical. I'll move to the first. Write these questions, write these values, then I'll move to the formula part. Write this question. In the first question, you have to find the nominal stress. Why they have written axial? Because we have applied an axial force. That's why they have written nominal axial stress. It's nothing but nominal stress we just discussed. Dimensions are given to you. Are you able to do? It will take hardly 10 minutes. What you are waiting for? Shall I move to the previous slides so that you can see the formulas? Hello?
Please.
Okay.
Ma'am,
Yes.
what is the difference between this initial thickness and initial height?
Wait. Which one? This one?
No, it says initial thickness and width of the this one. There are two things here.
Yes. A flat steel alloy bar has an initial thickness of 10 mm. Means original its thickness was 10 mm. And initial width of 60 mm.
Ma'am, it doesn't say anything about elongation, only width and
You
thickness.
have to find the area na. Elongation will come to the next question part na. Elongation will come to the next part. For the stress, you don't need elongation na. For the stress, you need what? Force per unit area. So how will you find the area? Width into thickness. Is it or not? Yes or no?
Understood.
My screen is visible?
Ma'am,
My screen is visible?
No, ma'am.
No.
No.
Okay. Let me share once again. All of you do it by yourself. This is not, it will take hardly some minutes. Now it is visible. My screen is
Yes,
visible.
ma'am.
Okay.
Yes, ma'am. Ma'am, if you can please go back to the previous slide where there is the
Yes.
formula.
Sure. So this is your stress, normal stress. Nominal stress will be N by A naught. N is nothing but what? Your force, P. This will be a nominal axial stress, N by A naught. You have to find the area. I'm giving you a hint. You have to find the area. You have to get what is P. Because N is equals to P, whatever the normal force will equals to P, whatever the load we are applying. As per this formula, N is equals to P. Whatever be the load we are applying, that will be equal to normal force. So this is the formula for sigma equals to N by A naught. Here you can write P by A naught. Then now for the strain, we have elongation by L naught.
Ma'am, is it 1 by 10? No.
By 10 unit.
One second.
Tell me the unit. You're telling the nominal stress or nominal strain.
Ma'am, kilonewton per millimeter square. Per millimeter. Oh yeah, per millimeter square. Kilonewton per millimeter square.
Answer what? Okay. You're telling me the stress 1 by 10 kilonewton per meter square.
Square, ma'am.
Okay. Do one thing. All of you write your answers in the chat box. For the stress, write your answer in the chat box.
Ma'am,
Yeah.
is it 1 by 10 kilonewton per millimeter square
Kilonewton per millimeter
for the
square.
stress?
Okay. Do one thing. Write all
Stress.
of your answer in the chat box. Let's wait for 1 minute. Let's wait for 1 minute. Others what they are doing.
Do we have to convert into any SI unit or
Yes,
something like
you
that?
can convert. You can convert in Newton per mm square. Then you can convert into MPa.
Mm.
You can do that. No issue. Done. Most of you got correct answer. Who wrote kilometer? Okay, this will be kilonewton. Roll number. Good. Okay. So the answer is yours. The 1 by 10 or 0.1 kilonewton per mm square. Okay. And you can convert that into Newton per mm square. Then you can also take it to MPa, megapascal. So next, let's move to the strain part. Next question. Good. All of you wrote 1000 Newton per mm square. Good. Very good. All the answers are correct. Now let's move to the strain part. Do the strain part. Dimensions are given to you. Or a flat steel alloy bar has an initial length of 900 mm and subjected to, okay. Oh, my screen is not visible again. Write down these questions. Huh? You should have these questions. Six kilonewton per mm square. Anyone? Next. Fast, fast. How much you have taken, Okato? How much delta you have taken? The question was given as a flat steel alloy bar has an initial length of 900 mm. Okay. And subjected to a total axle length is the bar elongates to 0.5 mm. Okay. So I told you this will be a dimensionless number. It will be a dimensionless quantity. So how you got the unit? I told you this will be dimensionless. I'll explain once more how this becomes dimensionless. One more answer I got. 1 point. Where is that screen? 0.0 correct. 0.005. So I'm sharing the answer part. Okay, good. All of you tried. Good, very good. My screen is visible. Is my screen is visible?
Ma'am.
Yes.
Yes.
See the answer. See the answer. Answer is in front of you. Sigma equals to P by A naught. So P is nothing but your N, right? N is nothing but your P. So question is given to you that a flat steel alloy bar has an initial thickness of 10 mm, the thickness, and an initial width of 60 mm. So from here you will get your area. 10 into 60 mm will give you your area of the bar. It is subject to a total axial load in tension of 60 kilonewton. See, tension, so this will be, your answer will be positive. So 60 is your nothing but P. So we got P, we got area, we can use this formula. Sigma equals to P by A naught. So this how, put the values, then these are the values, these are the conversions. Then let's move to the next question. The same flat steel alloy bar has an initial length of 900 mm. So our L naught is nothing but 900 mm. And when it is subjected to a load of 60 kilonewton, it elongates. How much? 0.45 mm. So this is our delta. This is initial was 900 mm, and what was the change in length? The change in length was 0.45 mm. So this, see here, this mm and this mm will cancel out. So this quantity will become automatically dimensionless number. So always remember, stress has dimension of Newton per mm square or kilonewton per mm square or MPa, but strain is always a dimensionless number. Okay, dimensionless quantity actually. So hope this part is clear. What we did today. Basically, we review what was the normal stress. Okay. Then we discuss the various stress, normal stress, nominal stress,
Ma'am,
stress. Yes, yes, yes.
10 into 60. Can you explain this one? 10 into 60 for the straight.
10 into 60. For this part.
Yeah.
This is the length now. In strain, what is the formula? See, what is the formula in strain? Original length by, change in length by original length. So in that, yeah, only length. Here we have to consider only the length, because length part will change your, there is a change in your length in strain part. See the formula, only length part we have to consider. The strain will always, strain is change in length by your, let me one out. Only the length part. So your strain is nothing but how much there is a change, or you can write in this way also. Change in length by original length. Suppose I have given you a rope, or suppose I have given whatever 10 meter. This is a 10 meter bar. Suppose 10 meter bar. Okay, its original length is 10 meter. So here it will be 10 meter. When I pull this bar, suppose I pull this bar, I've stretched this bar, and I got a new, and this bar has, it's stretched to this amount. Now if you measure the length,
Ma'am, I got it.
sorry,
I got it now.
okay. Anyone else who didn't got it, this part? Hope everyone got this part. These two numericals were very easy, I guess. No issues with this. Just remember this part. Many of you used to do mistakes with the unit part. Hope this part is clear also. In the next class, we'll discuss the stress strain curve. Okay, we'll discuss what is stress strain curve. Anyone remember what was the stress strain curve? What? Anyone remember stress strain curve? Engineering mechanics first class, I guess. Anyone remember? No. Okay, all of you can do. I'll stop sharing my screen. All of you can do. You can write your roll numbers in the chat box so that I can. From the next class, I'll be a little fast. Okay, if I go in this rate, so your course will not complete. Course will, you will be lagging behind. So from the next class, I'll go bit fast.
Any update on when the college will reopen?
College will be open from September 1, I guess. But what about you guys? I don't know. For us, it will open by 1st September.
So, ma'am, if it reopens, the teachers will go to university.
Teachers will?
You guys will go to university,
Yes,
like for
yes.
teaching.
We are going university now also, time to time, in shifts. But as from that time, we'll go